Hello, welcome to another Cosmology talk. Today we have Charles Dalang, who is a PhD student at the University of Geneva. He'll be talking today about the dipole and isotropy tension, which is something I think I've been sleeping on a little bit. It's tricky with tensions in lambda CDM because there's so much cosmological data now and so many cosmologists analyzing it from so many different directions that you do expect some tensions to arise. But at the same time, if there's new physics, if lambda CDM is not correct or not complete, you expect that new physics to first show up as tensions. So one needs to take the tensions very seriously, but not necessarily throw out the entire model just because they exist. And of course, science works via scrutiny, and the best models survive the toughest scrutiny or get replaced by better ones. So one really does want to scrutinize the data and lambda CDM as much as possible. Charles has an interesting take, not completely dismissing the tension, but looking for what already known physics might be out there that could explain what's causing it to arise. So welcome, Charles. Do you want to start by telling us what it is that is described in the paper?
Sure. Thank you very much for the introduction. So, we have this recent paper on the cosmic kinematic dipole tension. So people have tried to measure the velocity of, the observer, the sun, us, in the universe in different ways, and one with the CMB and one by observing sources and counting the number of sources in different regions of the sky. Both of these measurements are affected by the velocity of the observer, and the values that people get are different. In one case, you get 369 kilometers per second in one very precise direction. And in the other case, you get a factor of 2 of this in slightly different directions. And the tension has increased over the years and has reached 4.9 sigma in a paper by Secrest et al. About last year. And so what we did is we tried to re-derive a theoretical expression for the kinematic dipole that we thought we could improve.
So if there were only two things people remember from this video or the paper 6 months from now, what would you want those two things to be?
What we showed, what we think is very important in this paper is that, the universe evolves, and you should really take into account actually the distribution of your sources with redshift if you want to compute accurately what is the expected kinematic dipole from source number counts. So this is one thing that I think is really important, has been ignored for a long time. Maybe a second thing is that the universe is in expansion, so you cannot just do a special relativity calculation and expect it to work. You should really do a general relativistic calculation and be very careful.
Why did you do this? What is the background? So maybe a little bit of detail about how this had been measured, first of all, via the CMB, although maybe people are more familiar with that. And then second of all, I think it was quasars was the measurement that has given the biggest tension. And then why do you think that the particular effects that you're talking about had been neglected until you guys came along?
Yeah, people have measured, the CMB a long time ago and have observed that there's a very strong dipole, which is 2 orders of magnitude stronger than the other anisotropies in the CMB, and has been interpreted, as the motion of us towards a direction. So if you have a velocity v naught, and you move towards a direction, then you're just going to Doppler shift the spectrum in this direction, and you're going to, blue shift in one direction and red shift in the other direction, and it naturally gives rise to this dipole pattern. So here we're moving towards this very precise direction, and from this you can extract the amplitude of the velocity, also the direction, and the velocity of this is 369 kilometers per second, which is typical for the movement of a galaxy and the universe. Actually, in the lambda CDM universe, people have made simulations and also observed this kind of velocity, so it's not very surprising. There are also consistency checks which you can make for the CMB with higher order multiples, second order effects in the velocity. So there's kind of consistency checks which tell you, this dipole is mostly attributed to the velocity of the observer, but you could also expect that there's some part of it which is intrinsically there, but which is expected to be 2 orders of magnitude lower from early universe physics. Early universe physics predict a scale invariant power spectrum, and so the most natural thing is to expect it to be mostly kinematic.
Just before we switch, can I say something that I think it's me being a bit silly, but I've always found that the convention that has become the convention for the hot and cold spots of the CMB is the wrong way around, right? Like the hot spots are red and the cold spots are blue, whereas blue light is actually hotter than red light. And when you were literally now saying, because of the dipole, you get a red shift and a blue shift, I think in this plot, the red shift is plotted in blue and the blue shift is plotted in red.
Yeah. Yes, that's correct. Yeah, you're right. Yeah, the color code is a bit confusing.
Well, it's not confusing because I think everyone thinks of red as hot and blue as cold. It's only confusing if you bother to actually to be annoying like I just was.
Yes, so the other way that you can measure this velocity is by counting the number of sources that you have per solid angle omega. So here I call this delta, and it's something which depends on the direction you're looking on the sky, which is this n vector here, n hat. And it's just the difference between the number of sources per unit angle that you see in one direction above a certain flux density, because every experiment has a flux cut. You cannot observe something if it's too faint. And you subtract the angular average. So you subtract the mean number of sources that you see on the sky per unit pixel. And this is something you can go out and measure. And it depends on a very precise way on the velocity. So here I'm showing you a map from actually this Secrest et al. Paper 2021, where they observed quasars over the sky. And you see you have around between 30 and 90 sources per square degrees. And they sort of smooth this on the right panel so that you can see there's a blue region and a region maybe on the right, which looks a bit more red. So you also see the effect, a similar effect, more sources in one direction. So why is this the case? Well, there are two effects. There's one effect, which is the aberration of angles. So if you go towards one direction, the angles, they sort of get contracted. And this gives you this factor of 2 here for the delta, which is the Ellis and Baldwin derivation, which dates from 1984, so way before we had all these measurements with quasars or whatever. And then you have this other effect, which is a magnification bias and the spectral index. And it's really Doppler effect. If you move towards these sources, well, some of these sources will get Doppler shifted. They will go just above your flux cut, so you have this X which enters, and you also have this alpha because the spectrum of your quasars is not flat. It has this power law shape. So these two effects sort of combine and give you this X times 1 plus alpha. So this is really a calculation which you do assuming it's nothing. I mean, it's special relativity.
And so in the direction you're moving away from, some things get redshifted and then below your flux cut, I guess. And so then you see slightly more where you're moving towards and slightly fewer where you're moving away from.
Exactly. And so you see it depends also on the velocity of the observer. So if you have v equals 0, then you don't have this effect. But if you have certain velocity, then you have this.
But I guess maybe foreseeing the punchline well in advance, there looks like there's a very strong degeneracy here between alpha and the magnitude of v naught. So if one wants to claim they've measured the magnitude of v naught, one wants to make very carefully that they've measured alpha as well.
Sure, and the thing is that alpha is something which depends, on each source. If you look at this Secrest et al. Paper, they have a whole distribution for alpha. It varies between 0.5 and 7. So there's a whole range. And what you can do is take the average of this, which we'll see is correct, provided that X is very constant. But if it's not, then it doesn't really work. And so people have been around and measured this thing and then did the computation, how much do you expect? And they found typically this factor of 2. And the reason why we jumped in here is because the tension was claimed to reach 4.9 sigma. And at this point we thought, oh, maybe there's something going on here. If it's still 3 sigma to, 3 sigmas, they come and they go. 4.9 sigma, it starts to become serious.
Yeah, 3 sigma is like a 1 in about 300 event. And you can imagine with thousands of cosmologists that a 1 in 300 thing will show up because we're just measuring all sorts of stuff and exploring the data in all sorts of different ways. But yeah, 5 sigma is more like 1 in a million, and there aren't a million cosmologists out there. So I guess it's more likely to either be new physics or like new subtleties within known physics. Maybe I'll ask a question I'm going to ask at some point just now, but I think literally the same day your paper came out, or maybe one day before or one day after, there was a paper claiming to measure this effect with supernovae and getting not that the observed velocity was twice as large, but like half as large or something like that. Do you have any thoughts about that? Does that fit within your kind of explanatory paradigm that they might just have different alpha and blah, 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 or is there something really weird going on?
They did it, but it was not so precise, right? They had events, they did it with supernova. The problem is that they don't have that many supernova. So I'm pretty sure their shot noise has to be quite large. Of course, if it goes a bit lower, then it questions, is this something real? I mean, it's surprising.
So is it possible though that with the effect that you're describing here, that the magnification bias changes with redshift, and then therefore you can't average the spectral index, that one might measure a smaller d-obs, or is it always going to be a bigger d-obs?
So I cannot tell what people observe. I mean, people observe what they do. I can just say something about what we expect them to observe, which is the Ellis and Baldwin computations certainly can give a result, but I'm not sure for supernova, because I don't think they have similar spectrum. But I mean, you can derive dipole formulas for any source. I mean, it can work for any source. Just this Ellis and Baldwin formula works if you have this kind of flux density, power law, and this magnification bias. You sort of expect to have this, but X can evolve with redshift also.
Yeah, do we want to get into the details now about precisely how you have taken this Ellis and Baldwin equation and pointed out that things are redshift dependent and that can affect the results?
So one thing we were really surprised when we saw this expression from Ellis and Baldwin is that it really does not depend on how far the sources are, and this seems a bit odd. I was really surprised. Turns out it does. Where there's one part where it does, but the kinematic dipole didn't seem like it depend on the distance. And so we thought, well, if it really does not depend on the distance, probably we can compute what is the dipole as a function of a distance. And then we integrate over the distance with the given distribution, and we should recover the result of Ellis and Baldwin. And so we did so. I skip all the details here, but I just give you what's the expected kinematic dipole integrated over co-moving distance. And what you see is that in general, if X depends on R and alpha also depends on R, well, you're not going to recover the Ellis and Baldwin result. If they are constant, of course, you will. If only X is constant and alpha is not, then you will have an effective alpha which will enter this thing, which is the average, which is fine. If you only have alpha which is constant, then it's the same, but you replace X with an effective magnification bias. But if they both somehow depend on distance, then the integral of the product is not the product of the integrals. And so it's a basic thing you probably learned in high school. And so it doesn't work. And so we thought, does alpha depend on R? Does X depend on R? Do we know? At least X, we have some sort of expectation that it depends on R. Alpha, we don't really know. There are some hints that probably alpha, if you would measure it at the source for the quasars of the Cat-Friese sample, probably does not depend on redshift, but as soon as you observe it, it's less clear. You have all sorts of effects which enter, K correction, stuff like this. And so it's not so clear. And in general, it's very difficult to measure co-moving distance.
And this f of r on this equation is then just like So
this f of r is the number density of objects at the position r. So it's integral. If you integrate over all distances, it gives 1. And so we thought, maybe we can derive another expression where we compute the kinematic dipole as a function of redshift, and then we integrate over all redshift. And in the same way, we should recover the same thing. And so what we find is this expression here in the first line. And it's not the first time that people have found this. So Roy Martins and Chris Clarkson and Chen have found this expression, the kinematic dipole at a fixed redshift. But they just forgot to integrate to match with what people observed. So we recovered the same result, and we thought, they observe things independently of the redshift, so you have to integrate over redshift. And you see this expression is a bit different. First of all, there's no alpha. There's still this factor of 2, which is, again, an angular thing. There's an h, which appears because the universe is expanding. So this is a perturbed FLRW where the only perturbation is the velocity of the observer. And then there's this last term here, which is the evolution bias, which traces the time evolution of the population of the sources you're considering. So for example, at the beginning of the universe, there are 0 quasars. So this F eval is 0. Then they start to get produced. We don't really know how, but they get produced, so their number increases, and so this F eval is positive. At some point, maybe they disappear faster than they get produced, or they merge, or something happens, and this F evolve can be negative. And so depending on how the population of quasars evolve, there's an impact on this kinematic dipole. And here I have two different plots to explain a bit this difference. So at constant redshift, what you do is that you access different cosmic times. Here on the right, I plot the observer here, and you have a line of constant redshift. And since you're moving in this direction, if you observe at fixed redshift, the source at S1 is a bit further away than the source at S2. And so it's at different points in the history of the universe. And so at one point it might be more negative, at one point it might be more positive, this F eval. And so, depending on if you have sources at low redshift or higher redshift, this F eval might play an important role. And so the difference is that if you're at constant co-moving distance R, then you do observe different parts of the spectrum. So this is the plot on the left. If you observe that a fixed nu 0, it will correspond to a different nu S1 and nu S2. So nu S1 might be here in red. You're just below the luminosity threshold cut. And here in the blue case, you'll be just above. So this is the analog effect at constant distance. But this doesn't appear if you're observing at fixed redshift. And so similarly, if you convert a bit this expression to an alpha and x, you recover the same result if they are constant, and if you can neglect boundary terms because there are some integration by parts which are going on in this derivation.
I guess here you're assuming that the peculiar motion of S1 and S2 can just be averaged over. That feels okay to me, but I guess you're trying to be very careful. Is there a more confident justification you can give for that rather than me just saying it feels okay?
Yeah, so the expectation is that all these points on the circle, they have their own peculiar velocity, right? That's what you think. Yeah, they will in general have their own peculiar velocity, and that would give probably an effect. The expectation is that it's going to average out. Yeah, I'm not sure I have any better explanation than this. We just ignored it.
And that means that's if someone wants to extend your work, that's maybe a natural place to look, perhaps. And
yeah, right. I mean, the movement of the observer is really something coherent that you're going to observe for all the sources, but for every other source, it's unclear what their velocities are going to be with respect to you. And
I mean, if it's linear, then it will average out. It's just if there's a nonlinear effect, then it might not average out. It might be that the ones that are moving towards you are adding slightly more than the ones that are moving away from you are subtracting or something. But I'd have expected that any degree of nonlinearity there would be quite a small effect.
So we're only considering linear perturbations in V naught. It could also give. Yeah, maybe a better answer is that it's going to give it's not going to give a dipole signature. It's going to, be present in many other multiples of your signal. Whereas V naught is really something which is a pure dipole. I mean, so then redshift evolution. So the question, is it clear that, alpha and x are constant? Well, for x, at least we know, like for many different sources, this is something which evolves with redshift. And for example, here we have two plots for the EBOS quasar sample, which it's only 13,000 sources, and here you see that it evolves by a factor of 2, roughly, between redshift 4 and 0.6. So there is some evolution here, and if it does evolve also for alpha, well, we don't really know. There's no convincing measurements for this, at least for this sample, so we don't know.
Can you talk me through why the x as a function of z looks like this? Isn't this just a geometric effect? Why does it have like a piecewise thing happening at z equals 2?
Yeah, so this we took from this Wong, Butler, and Bacon paper. They measured these guys actually, and the way they fit it is with a piecewise parametric thing, which I think can be motivated because you have. I don't want to say things I'm not sure about. But the jump they have, they don't know where it comes from. They expect it to be continuous, and they claim its unknown systematics can come from something they don't know what. For the purpose of our talk, of my talk, it doesn't matter much. It's just to see that it evolves with redshift, And that, if you have this x as a function of redshift, then you can compute what is the kinematic dipole.
I guess what I'm getting really confused about is, can't I predict X just knowing lambda CDM? Why do I even need to know stuff about sources? Or does it matter how large their physical extent is on the sky? Like alpha, I appreciate is something astrophysical, but X I thought was purely geometric, but maybe I'm confused.
You see, it's this number of events above a certain threshold. So necessarily it depends on the details of your source. And so these guys they got this curve for EBOS, and we thought, since we have nothing else, let's try to use them for this Cat-Vise sample and see what it gives. This slide is slightly disconnected. It's just to say that there are some contaminations to the kinematic dipole, which are in this first line. So you have the kinematic dipole, which you expect from our own velocity. But then you also expect some intrinsic dipole in lambda CDM. You see, for example, if you are on the boundary of a void or on the boundary of a galaxy cluster, for sure you're going to measure more galaxies on one side of the sky than the other side of the sky. So this is this intrinsic part, which does not depend on the velocity of these observers. So it can be a vector pointing in another direction. And then, of course, there's shot noise contribution, which depends on the number of sources that you have. So, of course, if you have only one source, you're going to say there's a dipole in this direction. It's probably going to be wrong. So this is called shot noise, and it's an effect which goes down with 1 over the square root of the number of sources. And so these you can compute. For example, here, they also were able to extract in this Secrestenal paper a redshift distribution of their sources. For a subsample, they were able to cross with SDSS, and they have this plot here where it gives you the number of sources per redshift bin. And if you have this, you can compute what is the expected intrinsic dipole in lambda CDM, and it's small. It's very small. And in this situation, you can compute what is the expected dipole that you're going to measure given these two variant sources of variance, and also what is the expected variance. So you're also not going to expect to have the dipole point exactly in the same direction as the CMB dipole. So I put a little plot here. You have this kinematic dipole, which you expect, but you have some spread. It can be somewhere in the blue region, more or less. So they also measured in this paper the X parameter, but independently of redshift. So they get sort of an average effective magnification bias, which is roughly 1.7. And then you have many curves which can give you this 1.7. So we decided to play around with extreme curves. You have the flat scenario, you have this purple line, which looks quite similar to the one of EBOS. Okay, it's really, let's play around. The effect of changing this curve on this kinematic dipole doesn't change much unless you have many sources at very low redshift, because this R here is going to be very small and then it's going to amplify the effect. But if you have sufficiently high redshift sources like they do in this Cat-Vise sample, it doesn't impact much this thing. What can impact is the evolution dipole. So then we just try to reproduce a curve like the black curve, which reproduces quite well the EBOS, but you see that we corrected for the jump because we are unhappy with the jump. So we produce this black curve here, and what happens in this case is you can compute the kinematic dipole and you go down for the expected tension. So you take into account shot noise and clustering. The tension goes down to 2.6 sigma. But of course, whether this evolution bias is representative of what happens for Cat-Vise, we cannot tell. Probably it's not very accurate. Probably it's different. We just try to play around and point out, if you have a slightly smaller evolution bias, like this blue dashed curve here, you go down to 2 sigma, and if you're even slightly smaller at low redshift, then you go down to 1 sigma. To reproduce the 4.9 sigma, you have to get this yellow line, for example. This yellow line here reproduces the 4.9 sigma tension which is observed, which may be the case. It may be. We cannot tell. It's just there's a rough factor of 2 between quasars at redshift 0.6. Between the black line and the yellow line is a factor of 2. So is it reasonable to expect this factor of 2? Honestly, we cannot tell. You have to go out and measure it and see. But it's just, there's an effect. If the population of quasars evolves with time, then it impacts the kinematic dipole. And so we thought this was sufficiently interesting that people should know about it and go around and measure what is the redshift dependent dipole and integrate over redshift.
So this F evol here is the same parameter as what EBOS measured here, but because the Sekrestadal sample was not from just like the one telescope with very well understood systematics, it's impossible from measurements determine what F evol should be for the Sekrestadal sample.
Yeah, exactly. We can just not tell.
I've gotten a little bit confused here. So the alpha parameter that was there at the beginning has kind of been factored into this F evol in some way in the kinematic one. Is that right? Or
yeah, if the mapping was so simple, we would have given it. Yeah, we just don't know what is the mapping between alpha and F evol. It's somehow mixed. It has to mix a bit. It's not clear, but it would be really good to have it.
So what is the changing X of Z do? How does that affect things?
It does affect it, but less. It affects less the dipole. So here, for all the curves on the right, we took the blue line, which is linear increase in this magnification bias.
And so the summary is that if evol, which you described earlier, if the number of quasars sort of coming into existence and number of quasars leaving existence, I guess here, or net number is following this particular pattern, then if you average over redshift, you will expect some sort of kinematic dipole that's quite different to the actual, assuming that lambda CDM is correct and the universe is homogeneous, different to the God-given dipole.
And you see the point where it flips sign is very important. So here it flips sign around redshift 2. So if you have more sources below redshift 2 or above redshift 2, it changes the sign of this evolution part of the dipole. So it seems to matter. And so the Sekrestadal paper, they have more sources below redshift 2 than above redshift 2. But again, we don't know what is the evolution dipole for this situation. But if it has a similar shape, then you could expect it to drive the dipole higher.
Yeah, I guess in principle, if they were here, they could equally argue that if it had a different shape, that it could actually be that this is a 7 sigma discrepancy.
That's actually what they said. So we had this discussion with Subir Sarkar and Sebastian von Hausiger, who are 2 members of this group. And exactly, that's what they pointed out. You know, the curve could be well above also this EBOS. And we said, yeah, that's right. So we added actually this yellow curve to show that, yes, indeed.
What are the prospects for like measuring that somehow? Is it possible? Or do we have to wait for some future survey that has the power to do this? Or is that outside your scope of expertise?
Yeah, so it is very much outside of my scope of expertise because I do calculations. I don't measure anything ever. But yeah, I think it's a great opportunity. It provides a cross check to check if this tension is real. It could be higher, it could be lower. I mean, it deserves to be checked. So what you need to do is to measure the number, to do the same measurement, but also to access redshift. So this can definitely be done. I mean, and quasars is cool, but I mean, there are plenty of also other objects which you could observe. Yeah, there's this DESI. They also plan to measure many, many quasars.
And so the reason you can't do this with EBOS, because with EBOS, obviously you do have this F-evol, like the shot noise would be too big. They just don't have enough quasars in their sample, or?
Yeah, so there are several things which you need. You need a good sky coverage. If you don't see enough of the sky, then there's no chance you can measure. Well, you can measure the dipole, but it's probably not very good. And the second thing is you need enough sources. For this sample from EBOS, they had only 300,000 sources, and in this case, you're completely dominated by shot noise. You really need above 1 million sources.
And how much did Sekrest et al. Have in total?
They had 1,300,000 roughly. So yeah, these are my conclusions here. So we thought that measuring the redshift of source counts allows for an alternative prediction of the kinematic dipole. So I think this is an important message that we want people to study and go out and measure. And then maybe this is slightly oriented as a sentence. for reasonable time evolution of quasars as extracted from EBOS, the tension may be alleviated, but it may also be strengthened.
Yeah. I mean, that second sentence, I think, is priors do a lot of work there. If you're convinced a priori that there is no tension, you can read this and be like, yeah, okay, there's no tension. If you're not convinced there is no tension, then you have to be like, why would I expect the Sechrist et al. Quasar sample to be so similar to the EBOS quasar sample? There's no a priori reason I should. So therefore, the tension is exactly what it was. but it's certainly it's certainly a plausible explanation that should more work should be done to try and extract it. I guess the next question is then like, what comes next? Do you and Camille have your own kind of calculational things you're expecting to do next? Obviously, from the observational side, if people could go out and measure F-eval for a large number of quasars, please go and do it. But and you mentioned other sources. Are there other observational groups who you think should be or could be kind of weighing in on this? What's necessary? Lots and lots of sources and a well understood, I guess.
Well measured redshift, spectroscopic redshift would be really nice, and good sky coverage. So lots of sources, good sky coverage.
So why is this not possible with galaxies? Why are they doing it with quasars?
It is possible with galaxies. Yeah, I just don't think the spectrum of galaxies is not the same as quasars. So this power law thing doesn't work. There's no alpha. There's no spectral index. But certainly our formula you could apply to galaxies.
Cool. I guess if there's not a huge slope, you might not get lots of things scattering in or out of. So it might be that the expected magnitude of the dipole is very small because whichever direction you look, you're not getting sources scattering above your flux cut or below your flux cut, perhaps. I'm not sure.
Yeah, so it depends both on X and alpha. But if X was 0, it would be perfect because then you would only have the angular thing and you'd have nothing to measure. It would be 2v0. So you'd measure the dipole and you could extract directly what is.
Well, possibly, but it might be that the size of that is too small, that you need X to be very large before this becomes actually measurable, if that makes sense. It might be more easily modeled with X equals 0, but much more difficult to measure, perhaps.
Yeah, I don't think there's any source which has X equals to 0.
Okay, yeah. So, do you and Camille or other collaborators have anything planned on this topic next?
So we do not. Camille and I, we have this project out. We didn't think yet about an extension. There's no real obvious extension for us. It's just that point out there's a different alternative prediction. And wait for people to do the measurement.
Okay, well, the last question then is what work being done in cosmology at the moment do you think is particularly underappreciated by the rest of the community?
Yeah, I find this question very difficult. I think many things are really well appreciated.
We're perfectly calibrated as a community. Everything's getting exactly how much appreciation it deserves.
No. I mean, perhaps people doing observer-dependent cosmology, I think, is really a thing which people should be very careful about. For many years we've been with the homogeneous isotropic assumption. We're just a random observer somewhere in the universe, very average. Turns out we are a very specific observer. I mean, we have a velocity in a given direction. We have maybe a void next to us. So I think more and more people should think about these things when they work on cosmology, not simply assume we're perfectly Copernican observer in a homogeneous and isotropic universe. I think in this sense I agree very much with Subir Sarkar, who is arguing we are not Copernican observers. I think that's very true.
Cool, that's a good answer. Yep. Well, thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified of new videos. Click like to help with various YouTube algorithm-y type things. If you have any questions or suggestions, leave a comment. And other than that, thanks, Charles, for the great talk.
Thank you.